Hi, in this question, we need to draw the shear force and bending moment diagrams for the shaft supported at bearings A and B. The shaft is subjected to vertical loads of 2.2 kilonewtons, 3 kilonewtons and 0.8 kilonewtons. The given shaft is hanging beyond the support B. Therefore, it is an overhanging beam. At point C, 2.2 kilonewtons is acting. At point D, 3 kilonewtons is acting. At point E, 0.8 kilonewtons is acting. And these two bearings, A and B, are exerting reactions RA and RB respectively. The reactions RA and RB are acting in the vertically upward direction, whereas the remaining loads are acting in the downward direction. Therefore, let us consider the equilibrium of the entire shaft and resolve the forces vertically. That is, sigma Fy is equal to 0. Let us write the upward forces are equal to the downward forces. That means Ra plus Rb is equal to 2.2 kilonewtons plus 3 kilonewtons plus 0.8 kilonewtons. Ra plus Rb is equal to 6 kilonewtons. Let us consider this is our equation number 1. Here, this Ra and Rb are unknowns. We need to eliminate one of the unknowns. To eliminate one of the unknowns, let us take moments about the point A, that is, sigma Ma is equal to 0. Means that the algebraic summation of the moments about the point A caused by all the forces is equal to 0. The moment caused by the force Rb multiplied with perpendicular distance is 1.2 meters plus 1.5 meters plus 1.3 meters. That is, the distance between the point A and B is equal to 2.2 kilonewtons multiplied with the perpendicular distance is 1.2 meters. That is the distance between the point C and A plus 3 kilonewtons multiplied with the perpendicular distance is 1.2 meters plus 1.5 meters plus 0.8 kilonewtons multiplied with the perpendicular distance is 1.2 meters plus 1.5 meters plus 1.3 meters plus 1 meter. On calculation, we obtain the reaction exerted by the bearing B, Rb, is equal to 3.7 kilonewtons. Plugging this value in the equation number 1, we obtain Ra, that is the reaction exerted by the bearing A, is equal to 2.3 kilonewtons. We will do the calculation for shear force and bending moments. Let us consider our section here somewhere else, just right of A. That means this is the beam under consideration. Here, the reaction Ra is acting in the upward direction. That means the left upwards is considered as positive. Therefore, the shear force at A, Fa is equal to plus Ra. The magnitude of Ra is 2.3 kilonewtons. Now, let us move our section to the point C. That means just left of point C. We are going to place our section here. This is the beam under consideration now. How much force is acting? The shear force at the point C, Fc, is equal to 2.3 kilonewtons. No other forces are acting in the upward direction or downward direction except Ra. So, this is the magnitude of the shear force at the point C, just left. Now, coming to the just right. Just right of C, that means our section is here somewhere else. The shear force at the point C, Fc, is equal to 2.3 kilonewtons minus 2.2 kilonewtons. On calculation, we find that this is 0.1 kilonewton. This is just right of C. Now, let us move our section to the point D. That is just left of D. This is our section now. How much force is acting? The shear force at the point D, Fd, is equal to 2.3 kilonewtons, that is Ra, minus 2.2 2 kilonewtons. That's all. We are considering just left of D. Therefore, on calculation, we find that FD is equal to 0.1 kilonewton. This is just left of D. Now coming to the point just right of D. FD is equal to 2.3 kilonewtons minus 2.2 kilonewtons minus 3 kilonewtons. On calculation, we find that it is negative 2.9 kilonewtons. This is just right of the point D. Now let us move our section to the point B. Here also there is a point load or concentrated load, that is the reaction RB. Therefore, we are moving our section to the point B just left of B. The shear force at the point B just left of B will be equal to the same magnitude, that is negative 2.9 kilonewtons. This is just left. Now coming to the point FB just right is equal to 2.3 kilonewtons minus 2.2 kilonewtons minus 3 kilonewtons plus the magnitude of RB. RB magnitude is 3.7 kilonewtons. On calculation, we find that FB is equal to 0.8 kilonewtons. This is the magnitude of the shear force at the point B just right. Now let us move our section to the point E just left of E. Just right of E, there is no beam at all. Therefore, the shear force at the point E, FE, is equal to 0.8 kilonewtons. Now let us determine the bending moments at all these points. Bending moment at the point A and the bending moment at the point E, MA is equal to ME is equal to 0. Now coming to the point C. At the point C, the bending moment MC is equal to how much force is acting? This RA multiply with this 1.2 meters. That is 2.3 kilonewtons multiply with 1.2 meters. On calculation, we find that 2.76 kilonewton meter. This is at the point C. The sign convention is very important. Since this is an overhanging beam and between the points A and B, the loads 2.2 kilonewtons and 3 kilonewton causes a sagging moment. Therefore, it is positive. Now coming to the point D. The bending moment at the point D, MD, is equal to this 2.3 kilonewtons multiply with 1.2 meters plus 1.5 meters minus 2.2 kilonewtons multiply with 1.5 meters. On calculation, we find that MD is equal to 2.91 kilonewton meter. Now coming to the point B. That is, the bending moment at the point B, MB, is equal to 2.3 kilonewtons multiply with this 1.2 meters plus 1.5 meters plus 1.3 meters is 4 meters minus 2.2 kilonewtons multiply with 1.5 plus 1.3, 2.8 meters minus 3 kilonewtons multiply with 1.3 meters. On calculation, we find that the bending moment at the point B, MB, is equal to negative 0.86 kilonewton meter. Already we have determined the bending moment at the point E is 0. We will draw the shear force diagram and the bending moment diagram. Whatever the magnitudes we have determined for the shear force and bending moment at various points, we will plot it. Shear force at the point A is equal to RA, that is 2.3 kilonewtons. Between the point A and C, there is no other load. Therefore, here also it is 2.3 kilonewtons just left. Just right, we consider this load also. Therefore, there is a drop in shear force here. As a result, we are obtaining 0.1 kilonewton. just right of the point C. This one remains same till the point T just left. That is 0.1 kilonewton. Because of this 3 kilonewton load, there will be a drop here. Therefore, here the magnitude is negative 2.9 kilonewtons. This 2.9 kilonewtons remains same till the point B. That is just left of B. Just right of B, we include this reaction also, that is RB. As a result, the shear force at the point B becomes 0.8 kilonewtons and this one remains same till the point E, 0.8 kilonewtons. This is how we draw the shear force diagram and shade the complete area. This area is positive, this also positive, this is negative and this one is positive. Now coming to the bending moment diagram. The bending moment at the point A and E is 0. Here it is 0, here also it is 0. The bending moment at the point C is 2.76 kilonewton meter. The bending moment at the point D is 2.91 kilonewton meter. Coming to the point B, the bending moment at the point B is 0.86 kilonewton meter negative, and we shade the entire area. As far as the bending moment diagram is concerned, this portion is positive and this portion is negative. From these two diagrams, we can find that at the point D, the shear force sign changes from positive to negative. Therefore, the bending moment is maximum here. Similarly, at the point B also, the sign of the shear force changes from negative to positive. Therefore, here also, there is a maximum bending moment in the opposite direction. There is another point in the bending moment diagram where the bending moment becomes 0 here. This particular point is called point of contraflexure. Thank you.